session. So, with the continuation of today's class, which we have carried out in the first half of today's session, that is in the morning half, we have discussed about the transport behavior in MOS transistor. Okay, so in MOS transistor, we have studied about how the transport behavior affects the MOS transistor and different aspects. So we've studied about how the transport mechanism are there, like when it is called to be ballistic transport, when it is said to be the diffusive transports, and we study different terms and conditions. So that is one of the important aspect as far as this VLSI, or mostly I can say CMOS VLSI is concerned. So now we'll proceed further, and in this session, we'll study about thin film fabrications. Okay, so these fabrications of thin film that we generally take into consideration in modern nanoelectronics devices. So basically, when we are working on the fabrications, so we need to work on different kind of materials. So one is actually one-dimensional material, second is two-dimensional material, and another is three-dimensional material. Okay. Now, thin film fabrication, when we say this thin film is considered to be a two-dimensional material. Okay, two-dimensional material means the material which has is like is considered to be in two dimension, and there is no third dimension of it. Yes, third dimension is that, but it is considered to be negligible uh, uh, compared to the other two dimensions. So that means you can say the this electron confinement is there in one direction, whereas there is free movement of electron in other two dimensions. So in that case, that is called two dimension. And in thin film, it considered to be two-dimension material, two-dimension material because the electron confinement is one direction. So that is it considered to be there is no third dimension of it, but there is a free movement of electron in other two dimension. Okay, so that is why it is called two-dimension material. Like I think you know one allotrope of carbon that is called graphene. So this is one two-dimensional material. So that is considered to be a two-dimensional material. Or thin film of graphene also sometimes we also produced in the lab. So so that is considered to be thin film. Okay. Now, in order to fabricate this kind of thin film, we need to adopt some of the physical process. So, what are the physical process? So, they are categorized into two broadly two processes, and they are mainly physical processes, and second one is the chemical processes. In physical processes, actually, there are some techniques are involved, and they are evaporation. Okay, so evaporation is one process, and under evaporation, many techniques are there, like thermal evaporation, MBE, which also sometimes we call molecular beam epitaxy, electron beam evaporation, also we call it E-beam evaporation, laser evaporation, and another one is ion plating. Similarly, after evaporation, the second one is coming sputtering. So in sputtering, there are three categories are there. There is DC sputtering, RF sputtering, that is radio frequency. RF is called radio frequency, radio frequency sputtering, and third one is magnetron sputtering. Similarly, in the physical process, the third category is spray processes, and under spray processes, it comes to be flame, and another is plasma. Okay, so under physical process, so thin film fabrications are categorized into two categories. One is physical processes, and second is chemical processes. And under physical process, there are three categories are there. One is evaporation, second one is sputtering, and third one is spray. Now, under evaporation, many things are there like thermal evaporation, molecular beam epitaxy, electron beam evaporation, laser evaporation, ion plating evaporation. Under sputtering, there are three categories are there, and one is DC sputtering, second one is RF sputtering, and third one is magnetron sputtering. Similarly, in the spray processes, there are two categories are there. One is flame, and another is plasma. Now, this is all about physical processes. Now, in the chemical processes, there are four categories are there, and they are chemical vapor deposition, that we call it CVD. Second one is called plating. Third one is called solgel, and fourth one is called ALE. ALE means atomic layer epitaxy. Okay, so this is fourth category. Now, under chemical vapor deposition, there are three types of chemical vapor deposition is there. One is thermal chemical vapor deposition. Second is MOCVD, that is metal organic chemical vapor deposition, and PECVD, that is plasma enhanced chemical vapor deposition. So there are three categories of CBD is there: thermal CBD, MOCVD, and PECVD. Metal organic CBD, thermal CBD, and plasma enhanced CBD. And under plating, electroplating and electrolysis are there. Okay, so these are some broad categories of thin film fabrications. So we'll study one by one. Okay, now in thin film deposition, there are some parts are very important, because this is very important that how the thin film depositions are done. So in thin film deposition, main thing is that we have different way of depositing the thin film materials. So one is our vacuum system, because vacuum is very important, because when we have a proper vacuum, so then we can able to deposit the materials with high purity. So good is the vacuum, that means we can deposit the materials with high purity. Then evaporation method. So evaporation method, we can evaporate any target materials, and then we can able to deposit on the substrate. Molecular beam epitaxy is that in molecular beam epitaxy, it is so accurate and so precise that the molecules by molecule, the atoms are deposited molecules by molecules, it is deposited on the substrate, and the vacuum is very good. So around 10 to the power minus 10 millibar we can achieve in the molecular beam epitaxy. So that is a very good approach in thin film deposition. Another is sputtering. Sputtering is a method where we can able to eject the materials, or you can say eject the atoms and molecules from the target material, and finally we can deposit on the substrate. Fourth one is chemical vapor deposition, where the chemicals entities are interact with each other, and finally it is deposited on the substrate. Laser ablation, where we use high energy laser beam to ablate the target material and then finally deposit on the substrate. Similarly, spray deposition is the plating, salt gel, ALE. So these are all thin film deposition techniques. Now we'll discuss one by one. Vacuum evaporation. In vacuum evaporation, what is that? The source material is very important, and in that cases, we heat the source material under vacuum until it evaporates or sublimates. Now, this vacuum is very important, because when we have a proper vacuum in the chamber, then the mean free path of the particles will be very high. Okay, so more the mean free path of the particles in the chamber, it will be very good to evaporate the source material and finally deposit it on the substrate. Now, why it is needed the vacuum evaporation? And first we need to understand what actually vacuum is. Vacuum is a region where there is no foreign particles are there. That means that is a clean, free. That will be a completely. There is no foreign entities in that region. So you can say, if you can consider the mean free path of the particle, then you can think that it is thousand of kilometer, the mean free path of the particle, because so there is no collision of the particles in that region. Okay, so that actually the evaporation systems here that we need to do. But in these cases, in the vacuum systems, as we need to deposit the materials on the substrate. That means the materials to be deposited from the target to the substrate. So we don't want any foreign particles to be encountered during this deposition process. So as long as the vacuum is good, we can able to evaporation. As long as the evaporation is good, or you can say the vacuum is good, we can able to deposit the material onto the substrate to make the film. So that is very important thing in a vacuum evaporation. So in the vacuum evaporation, heating a source material under vacuum until it evaporates or sublimates. Now the evaporant is deposited onto a substrate to form the film. Now this is also this vacuum evaporation is coming under physical vapor deposition. Okay. Now here in this case the deposition rate is very high and simple and easy to use. Now conductor materials in electronic circuits and devices, dilating optical coatings, these are all done by vacuum evaporation. So many brands think that the vacuum evaporation coming under PVD. So that we also sometimes call physical vapor deposition. And whatever the materials is evaporated, it finally deposited onto the substrate to form a film. And this is all. This, whatever the source material is deposited on the substrate and evaporates and sublimates. So that is under done in the vacuum condition. And so where it finds application, basically when we want to make electrode or make a conducting materials in the electronic circuits or devices, then this vacuum evaporation will be useful. The vacuum evaporation, this if you can see, think that the mean free path of the atoms in the vapor, then this mean free path of the atoms in the vapor is very very greater than the distance from the source to substrate. Okay, so you can easily guess that how vacuum is good, because the mean free path of the atoms in the vapor is greater than the distance from the source to substrate. Now, what is the deposition rate? How we can find out? So this can be found out from the Hurst-Sons relation. So Hurst constant equation, which we can say, so R by A is equal to C within bracket P double prime minus P divided by 2 pi MKT square root. Okay. Now what is C here? C is our evaporation coefficient. What is P double prime? That is evaporant surface vapor pressure. What is P? That is hydrostatic pressure. What is M? That is evaporant molecular weight. What is K? K is the Boltzmann constant. And what is T? T is the temperature. Or you can say it is the absolute degree temperature or in degree Kelvin. So this is where the deposition rate is generally is find out from this Hodge constant equation. So this is the way how we can. So it is C within bracket P double prime minus P divided by 2 pi MKT square root. So this is actually the and the different terminology I have highlighted here. So C is called evaporation coefficient, P double prime evaporant surface vapor pressure, P is the hydrostatic pressure, M is the evaporant molecular weight, K is the Boltzmann constant, and T is the temperature. Okay. Now, this vacuum evaporation, that if you take into consideration of evaporation coefficient, then larger for clean surfaces, then smaller for contaminated surfaces. Okay, so this is very important. The evaporation coefficient, when you take into consideration, larger it is larger for clean surfaces and smaller for contaminated surfaces. The deposition rate is such way that that greatly depends on the substrate to source geometry. So the deposition rate is very much dependent on the so substrate to source geometry. Now, non-uniform thickness on the surface also, the vacuum evaporation also depends. Now, due to distance dependence, the constant cosine law is cos theta by r square. Okay, so that is actually some. So, the evaporation coefficient, deposition rate, and non-uniform thickness on surface, that very important on the as far as vacuum evaporation is concerned. Now, the vacuum evaporation, the low energy process. So that means here it is the deposition material condenses onto the substrate with very less kinetic energy. So whatever this vacuum evaporation is done inside the this you can say in the vacuum environment. So it is a low energy process. So you can think that the kinetic energy is numerically equal to 0.5 electron volt. So the deposit material condenses onto the substrate with very little kinetic energy. Okay, so you can say whatever the deposition of the material is on the surface of the materials, or you can on the surface of substrate. So that is takes place with a very low energy. You can say the kinetic energy is only 0.5 electron volt. Whereas, if you think into consider sputtering technique, where the sputter deposition rate, the kinetic energy is greater than the 10 electron volt. Okay, so lack of step coverage area is also accounted in the vacuum evaporation process. So one part is clear that this vacuum evaporation is a low energy process where the kinetic energy is numerically equal to 0.5 electron volt. Now, this is very important that what are the actually evaporation sources actually we generally take into consideration. So, thermal evaporation, when we say, so there are some sources are we need to accompany. So, they are actually one is wire coil, and the second one is crucible, third one is boat, and third one is temperature control, that is electric current, and fourth one is difficult, that means high melting point materials uniformly heating, repeat changes of deposition rate, reaction between the source and heating container. So this is actually the some some points we need to take into consideration as far thermal evaporation is concerned. So basically the sources which we generally use in the evaporation process, so they are actually wire coil, second one is crucible, and third one is actually board. So these are actually source material on which our target material is placed. Okay, now using the heating element, uh, using with the use of thermal energy or heating processes, we can able to evaporate the materials from the target in the vacuum condition, and finally whatever the materials uh, is evaporated from the source material, then it is finally deposited on the substrate. Yeah, so these are actually about this can say evaporation sources. Now, electron beam evaporation, this is all thermal evaporation, where actually we use thermal energy to evaporate the material to finally deposit on the substrate. Now, in electron beam evaporation, we need a high energy focused electron beam to heat the surface material at a small area. Now, in the thermal evaporation, we use heat energy or thermal energy to to heat the target materials and finally deposit it on the substrate. But in electron beam evaporation, we use actually high energy focused electron beam to heat the surface material at a small area. Okay, and so that is actually a difference between electron beam evaporation and thermal evaporation. So, and as for thermal, compared to thermal evaporation, the electron beam evaporation has high energy. Okay, because the electron has high energy, so that can able to heat the source material at a smaller area. And as compared to thermal evaporation, the deposition rate is larger in electron beam evaporation. So that means larger deposition rate is there in the electron beam evaporation. Now, mm so what we need a high energy force in electron beam. So the water cooled container or cavity or hard. is generally associated with it. So, and that is why there is no source container reaction in that cases. And sweeping or oscillating the electron beam to heat the source material uniformly. So this is one of the process way how we can sweep or oscillate the electron beam to hit the source material uniformly. And multiple hard sources, the different source material, so where we can also do the things for evaporation of the material uh, from the source to the target, sorry, from the target to the substrate. Okay, so these are all multiple hard sources we need to take into account. Now this is actually a very nice uh, example, or you can say the images where you can see that how the film deposition techniques process. So this is a typical small volume electron beam source, and if you can see here, the electron beam is generated, and finally, whatever the source material is there, it finally evaporate the with the use of electron beam energy, it evaporate the source material and finally deposit it on the substrate. Okay, so this is actually typically the electron beam source. Okay, from here the only the electron beam energy generated. So this is actually typical small volume electron beam source. Molecular beam epitaxy, this is also one of its kind. So that means it's also coming under physical vapor deposition. In the molecular beam epitaxy, in these cases, this vacuum is very nice. So you can easily can attain up to 10 to the power minus 10 millibar. Okay, so the vacuum is very nice. So up to 10 to the power minus 10 millibar or 10 to the minus 11 millibar, you can able to attain. Now, what is meant by epitaxy? Epitaxy means the continuation of crystal structure from the substrate to the film. So that is called epitaxy. And this is actually molecular beam epitaxy is a single crystalline contaminant free film. That is actually, and even you can deposit and a single layer or monolayer uh, film onto the substrate by this molecular beam epitaxy. So you can able to deposit single layer um, of any two-dimensional material onto the substrate, or any single atomic layer growth can be possible with this molecular beam epitaxy when we want to deposit it on the substrate. And the small mismatch lattice constant up to less than 1% is also can be achievable in the molecular beam epitaxy. And as I said in the earlier, that here the vacuum condition is very high, so you can say 10 to the power minus less than 5 into 10 to the minus 10 torr, or 10 to the minus 10 millibar up to we can able to achieve. And non-epitaxy film, that amorphous or polycrystalline, so these are also can be deposited by this molecular beam epitaxy or MBE. Okay. So many important thing is that here molecular beam epitaxy is a physical vapor deposition technique. Here also we have to as the vacuum condition is very good. So that means you can easily can see that ultra high vacuum condition, so where our purity is very high. So 10 to the power minus 10 we can able to achieve in this molecular beam epitaxy, and finally we can able to achieve a very good two-dimensional material onto the substrate. So, if we even if we want to develop a single layer or monolayer uh, material onto the substrate, we can able to do deposition accordingly. And in these cases, our molecular beam epitaxy is a nice choice to deposit the material onto the substrate. That is why it is the purity is very high, and as it is a ultra high vacuum condition is achieved in this condition, so you can get a less contaminant free film in this case. So you can say a less content free film can be developed and can be deposited by this process. Now, in MB film growth, that is molecular beam epitaxy film growth, the single crystalline substrate with lattice matching to the film can be achievable. Now, heating is done maybe up to 500 degrees centigrade to 550 degrees centigrade for gallium arsenide, 700 degrees centigrade for to 900 degrees centigrade for silicon. So the heating to remove the surface contamination is possible. Okay, so generally in these cases we have to accompany the heat, because when we heat we can able to remove the surface contamination. So up to 900 degrees centigrade for silicon, 550 degree up to 550 degrees centigrade for gallium arsenide, and it can be possible we can heat the materials. Now what about the layer by layer growth, that is controlled by high speed shutters and thickness monitor. So generally the thickness monitor is there where we can able to monitor the film growth. So that is, can be done by thickness monitor. Now this is a read, that is we call it reflection high energy electron diffraction. So in this process we can able to know what thickness the two-dimensional material is deposited onto the substrate. This high energy electron beam, which is associated in molecular beam epitaxy. So this high energy is around more than 10 kilo electron volt. So up to greater than 10 kb, we can able to achieve in this process. And in this case, the grazing or small angle incidence is less than 3 degree, and low depth penetration less than 100 angstrom can be possible. So lateral order structure, surface structure symmetry, lattice constant can also be achievable in these cases. Okay, so this is also one aspect. And MB deposition system, load lock for substrate loading and unloading can be possible. Okay, so this is also one aspect of molecular beam deposition system. So we can load lock for the substrate for loading and unloading. Similarly, liquid nitrogen should to cool the wall, because during the process it is so much heat is generated, so we need to cool the wall. So in this case, liquid nitrogen is incorporated. Now, substrate heating, that is done by to clean the surface, and whatever the films are deposited on the substrate. So there is a thickness monitor, so that is monitored by read. So reflection high energy electron diffraction, we can able to see or measure the thickness onto the substrate. And so deposition rate also we can also measure by this thickness monitor. So film growth, the ultra high vacuum, that shutters to the control the flux, in situ analysis, and thickness monitor to control the deposition rate. Okay, so this is actually the how the deposition is made by molecular beam epitaxy. Now this molecular beam epitaxy, as I mentioned, so ultra high vacuum we can able to we can able to uh, we can able to attain. Ultra high vacuum means anything more than 10 to the power minus 10 millibar vacuum, so that we call ultra high vacuum. So this is, and what about the source material, that is source target material, that is placed in a Kunsen cell, that is called also called K cell. So if we want to make a group 3 group 5 semiconducting material, that means group 3 group 5 thin film materials, if you want to grow on the substrate, then molecular beam epitaxy is a very good choice. So like group gallium arsenide, this kind of thing, if you want to deposit it. So this group 3 group 5 elements, so like kind of thing semiconductive material we want to grow, and then molecular beam epitaxy is a very good choice. And so these are some of the aspects of molecular beam epitaxy. So this is actually how the molecular beam epitaxy looks like, and is a schematic symbol. If you can see here, So this is actually, if you can see, this is a solid source ion gun. This is electron beam evaporator. This is diffusion cell, and here the read gun where we can able to measure measure the thickness of the deposited film. So that is called reflection high energy electron diffraction. That is read gun. And this is X-ray source energy analyzer electron gun, and sample loss system, and this is sample transfer system. This is the shutter sample manipulator, and we can able to deposit it on the surface. So this is actually MB growth chamber, the schematic representation of this molecular beam epitaxy. And this symbol, this diagram which is showing here, the schematic diagram showing the main features of gas source molecular beam epitaxy. Okay, the group 3 molecular beams are supplied by molecular beam epitaxy effusion ovals, and the group 5 molecular beams are produced by thermal cracking of the gases like phosphine, that we call PS3, arsenic hydride ASS3, like this. Okay, so this is during the growth, where the pressure is 10 to the minus 2 torr to minus 4 torr, and this is heated substrate, epitaxial film, MB growth chamber. This is effusion oven, gas cracking oven, and group 3 solid source, and group 5 gas source. So here we can able to see. This is actually a vacuum pumping system for this molecular beam epitaxy growth, and as we need to attain the vacuum up to 10 to the power minus 10 millibar, so we need to have a good vacuum in the system. So if you can see here, where we have a cryo pump, iron gauge pump, a mechanical pump. All these pumps are associated with this and the growth chamber. Then only we can able to achieve this the vacuum into 10 to the minus 10 millibar. So this is the read screen. This is the sample liquid nitrogen is placed, because in that, during the process of this thin film deposition, so much heat is generated. So in order to compensate the heat, or you can say nullify the heat, or you can say to cool down, liquid nitrogen is the given, so that the heat can be dissipated out. So also these pumps are accompanied with it, because these pumps are essential to make a high vacuum in the system. Okay, because we can able to attain 10 to the power minus 10 millibar, 10 to the power minus 11 or like this. So this is very important. So this is actually the typical read pattern. Just like this, we can measure the diffraction beam. You can see in the electron gun and electron diffracted beams after this crystal surface. Read screens, specular spot we can able to see. So like this is actually our cases. Okay. Okay. Another thing is that we have a sputter deposition. So there is another deposition technique that we call it sputter deposition. So in these cases, this is also one kind of physical vapor deposition system. But unlike molecular beam epitaxy, here the bombardment and removal of the cathode materials with positive ions from a rare gas discharges take place. So that is. There is a bombardment and removal of the cathode material takes place with the positive ion from a rear guard discharge. So what happened in these cases? We have a target material, and another we have a substrate material. The target materials is generally is placed as a negative electrode, so that serves as a cathode materials, and the substrate is made a positive, or you can say anode. The substrate material considered to be anode. That means it is given the positive electrode is given. So when there is a electric field is given between this cathode and anode. So that means our cathode material is our target materials from where the materials to be spotted out. And when all the process is over, then the vacuum is created inside the system. Then after that, we introduce the rear guard elements. Rear guard elements like group 8 elements uh, this argon materials like this. So what will happen? This argon materials, when it is introduced in the vacuum system, so this is that becomes ion with the application of electric field, and these ions will be become positive ion. And this positive ion, as it's positive, then it is attracted towards the cathode materials. Now, the cathode materials is in our target materials. So, and the energy of the ions will be is so high because this ion is positive ion, and that our target material is negatively charged. So that is cathode metal. So negative positive attract each other. So that means the ions will directly attracted towards the cathode material, and finally it eject the material from the cathode surface by bombarding, or you can say it's sputtering out the material from the cathode surface. And finally whatever the materials is ejected out or sputtered out, then it is finally deposited on the substrate, and finally this thin film can be deposited. Okay, so this is how the sputter deposition generally takes place. So this is actually this also sputtering deposition is one kind of physical vapor deposition process, and this in this case the bombardment and removal of cathode materials with positive ions that form a rare gas discharge is possible, and originally developed to deposit refractory metals. And now the sputter deposition is able to deposit most of the materials. So sputtering deposition can be used to deposit most of the materials. So here also in sputter deposition system, we have a vacuum system, a pumping system, sputtering sources, vacuum sensors, a substrate holder, and gas flow supply. So these are also some of the you can say constituent in the sputter deposition system. The different types of sputter deposition systems are there. So in the sputter deposition system, so one is vacuum, one is pumping system, vacuum sensors, gas flow supply, and substrate holder. Okay, so the sputter sources that we see, so that is actually diodes or magnetrons. Okay, and direct current or radio frequency up to 13.5 megahertz can be we can able to accompany. Okay, and water cooled target, because target is heated by the is uh, is attracted by the ion. So this is made a water cooled target material. So argon gas is given, and plasma generated also can be possible. So because the this what you can say this uh, rare gas elements, that is like argon, is introduced in the system, so that will become ion with application of electric field, and then it is finally attracted towards the cathode material, and it eventually uh, ejects out some of the metal from the target, and finally it finally deposit it on the substrate. Okay, we'll discuss in our next class with the continuation of this course. So we'll stop it here.